Greetings everyone, welcome back, thanks for watching. So it's been a while since we've done a problem involving infinite series, and today I've got a gem for you. So we want to find the exact value of the series from n equals 1 to infinity of the arctan of 1 over n squared plus n plus 1. In order to get there, we're going to need some tools. Now, tool number 1 we just proved in the previous video. You're going to want to check that out. But we're going to use the fact that the arctan of x minus the arctan of y is equal to the arctan of x minus y over 1 plus x times y. Now from single variable calculus, we need to remember that the sum of an infinite series is exactly the limit of the nth partial sum. 3, we're going to have to recognize a telescoping series. And then 4, we need this classic result, which comes from this triangle. Okay, so I think we should dig right in. Okay, so let's see what we have here. So first we're going to start with this and then begin to rewrite this, and we're hoping to use 1. So let's check that out. Okay, so rewriting this, we get the following. So this, our original series, is equal to this, just by some minor algebra, a little bit of factoring. And I think on the side, let's see how we do space-wise. On the side, I want to write that rule just so you can see what I'm doing and it's crystal clear. So again, remember that the arctan of x minus the arctan of y is equal to the arctan of x minus y over 1 plus x times y. Now this is motivating all the algebra that I'm doing right now. Okay, so I see the 1 plus, and I see a product. I'm pretty happy with that. So just let's use the commutative law of addition, switch the order, right? So it looks a little bit more like this, and then we'll talk about dealing with the numerator. Okay, so that seems fine. One thing I want to note, so we're going to use auxiliary terms. Remember, that's when we add and subtract the same quantity. It's a useful form of 0. So for the numerator, let's just take note that 1 is equal to n plus 1 minus n. And that's pretty nice, right? Because if you think about it, this is exactly our x if you think about our form. And this is exactly our y if you think of our form. And so that puts us in a pretty good position to use this formula here. Okay, so let's rewrite this. We've got the series from n equals 1 to infinity of the arctangent of, it looks like n plus 1 minus 1 over 1 plus n plus 1 times n. Okay, and just note, this is x, this is y, there's x, there's y. Okay, so now we can rewrite this. So we have this, and we can rewrite it exactly like this. Okay, so we've got the series from n equals 1 to infinity of the arctan of x, but in this case x is n plus 1, so that's the arctan of n plus 1. And that's going to be minus the arctan of n, because that's our y, right? N is our y. And I'm noticing this difference. So what I want to do is, because I'm sort of reminded of telescoping series from Calculus 2, I want to find the sum of the first n terms. So we're going to do a little investigation. Okay, so we're going to investigate. And so 1, we're going to find S sub n, the sum of the first n terms. And we're hoping to find that maybe some of the middle terms cancel and this really is of a telescoping form. And if it is, then remember that the actual sum will be the limit of S sub n. That's how we define the sum of the series. Okay, so let's go for it. All right, so S sub n. Okay, so first I plug 1 in. So this will be arctan of 2 minus the arctan of 1 plus, now I'm going to plug 2 in. So if I plug 2 in, I'm going to have the arctan of 3 minus the arctan of 2. Okay, so arctan of 3 minus the arctan of 2. Seems good so far. Okay, so now we plug, looks like 3. We plug 3 in, we get arctan of 4 minus the arctan of 3. And I'm going to say plus dot dot dot, this pattern continues. So the very last term, that'll be when we plug n in for n, essentially, right? So that should give us something that looks just like this portion. So that'll be just the arctan of n plus 1 minus the arctan of n. And then let's go ahead and write the term before this. So if I write the term before this, this right here should go down by 1, and this right here should go down by 1. So yeah, writing the term before this, I should have the arctan of n minus the arctan of n minus 1. And then just one more before that. That'd be good. Okay, so the term before that, we should have the arctan of n minus 1 minus the arctan of n minus 2. And you're probably noticing as you write, we have some terms that are going to cancel. That's what we want with a telescoping series. So that's the arctan of n minus 2. You know, I've been using arctan notation for so long, I think today's the day that I appreciate this notation. I typically avoid it as not to confuse with reciprocals. I know it's all about context and what context you're in and whatnot, but I now appreciate this. So, okay, with that said, I'm going to commit. Let's commit to this notation. So that seems pretty good. So let's see what cancels. So it looks like this arctan of 2 is going to cancel with this. So that seems pretty good. So these are gone. And it looks like this arctan of 3 will cancel with this arctan of 3. This arctan of 4 would cancel with arctan of 4 a couple terms down. So it looks like this would stay. So this is going to stay right here. Nothing's going to cancel with it. And it makes sense if you look at the pattern of the sequences on the left side, right? You're never going to get down to 1, 2, 3, 4, etc. So that's going to stay. Now let's look for a canceling pattern on the far right here. So it looks like arctan of n is going to cancel here. It looks like arctan of n minus 1 will cancel. So this would certainly cancel, but hopefully you're noticing that this would stay. So this stays, and everything else cancels or sort of telescopes like a telescope that sort of collapses in, right? So it collapses in like a telescope. And so we get this very tidy version of S sub n. So S sub n is equal to, so let's write this with a positive term first so we don't have a hanging negative. So we're going to have the arctan of n plus 1 minus the arctan of 1. But where have I seen the difference of arctans before? Well, we just proved that, right? So remember, so we know that the arctan of x minus the arctan of y is equal to the arctan of x minus y over 1 plus x times y. Okay, let's use that. We have this. Let's write it as this. Okay, so that gives me the arctan of x, that would be x in our formula, right? So n plus 1 minus y, that would be our y, over 1 plus x, which is n plus 1, times y, which is 1. And that tidies up pretty nicely. So that looks like n over, what do you say, n plus 2? So n plus 2 sounds good to me. And we know that the limit of S sub n is the definition of the sum of our series, right? So we just needed to compute the limit of S sub n. So the limit is n goes to infinity of, actually let's call that S sub n. Actually, let's call it S. That's the limit of S sub n. So the sum is the limit of S sub n. So I'll write this a bit more detail, which is the limit as n goes to infinity of the arctan of n over n plus 2. And we can multiply the top and the bottom by 1 over n. Right, I can multiply by 1 over n over 1 over n. That's just so I can use limit laws. And so that's the limit as n goes to infinity of arctan of, how about 1 over 1 plus 2 over n? But as n gets large, this term will shrink towards 0. So in limit, this gets close to arctan of 1, which is exactly pi over 4. And that is the sum of our series. Pretty neat. I like that one.